Okay, so now that you have determined the calorimeter constant, you need to calculate the delta H of combustion, or delta U of combustion of your unknown. So I did a simulation for sucrose. This is the result I got. Okay, so my mass of sucrose is so this is my sample is sucrose. What's the mass of my sucrose? 0.9115 grams. What's the molar mass of sucrose? C12H22O11.
342.3. Or, yeah, 342.3.
342.3. Okay. So 342.3 grams per mole. How many moles of sample was burned then? Convert grams to moles. What do you do? What would it be?
0.9115 divided by 342.3.
0.9115. The mass divided by the molar mass gives you moles. How much wire was burned? According to the screenshot here, 0.0253 minus, so equals 0.0253 minus 0.0164. Okay, what's the known delta U for the combustion of wire in joules per gram? Do we have that earlier? It's just this number right here, right? So I can just say that is equal to this number up here. No, not that one.
Negative 5857.6.
Yeah, okay, so it's that number. Uh, so if I were to duplicate these later and replace it with your own data, you won't have to change that. That's fixed for the standard. So what's the actual Q wire for this run? Equals mass of the wire times
Times the known delta U divided by 1,000.
known delta U. So grams times joules per gram, that gives you joules. And then you divide by 1,000 to convert that to kilojoules. Okay. All right. So what's the delta T from the graph? Actually, let me not put this as a, let me not highlight this because this is not a formula that you should be keeping. You need to change this depending on your data. So this is going to be final temperature, which is 25.574 minus 24.205. So what, 0.369? What you're getting? Okay. So what's the C from the standard run? This is going to be equal to this calorimeter constant right here, right? Now, like I said, you have like 5 or 6 different trials to what from the bomb calorimeter we have in the lab for standard run. So you probably need to get some average and maybe put the average down here. Right, so you'll have to change that reference later. But for now, let's just use this number right here since I only have one run here in this calculation. So this is going to be equal to this number. Okay. But in the future, like I said, when you put together the different standardization runs, you should just have one average calorimeter constant that you're going to use for all your unknowns. Okay. So this is your calorimeter constant. All right. So now, how do I get Q sample plus Q wire given that I know my C cal, and my delta T? What was our formula? I now know C cal. I know my C cal, right? From the standard run. I know my delta T for this unknown run. So I just take the negative of that. I'm going to get the sum of Q sample plus Q wire. So for your unknown run, this is unknown, right? for the standard run, the C cal is the unknown. So it's just minus C cal times delta T. So what's my formula here? Equals minus calorimeter constant times delta T. And it should be negative, right? And again, if you compare the delta U for the Q for the wire and the total Q, how do they compare? Q for the wire again is negligible. But since you have that number, then just go ahead and use it. So now that I know Q sample plus Q wire, how do I calculate Q sample? This is the total Q, right? Minus the Q for the wire. So that's the Q for my sample. So what's the delta U for the combustion per mole of sample?
That number divided by mole all the way to the top.
Okay, so Q sample divided by moles of sample. Oh, not that one, this one, right? And that's already in kilojoules per mole. So that is the known delta U for the combustion of sucrose. Okay, now how do you calculate delta H? What's our balance equation here? Sucrose is C12, H22O11, solid, plus oxygen, gas, gives you CO2 gas, plus H2O liquid. What should be the coefficient of CO2 here? If I want this balanced. 12 CO2s, because that gives you 12 carbons on both sides. What should be the coefficient of water? 22 times 2 would give you 44 hydrogens. 11 waters. 11 times 2 would give you 22 hydrogens. And what should be the coefficient of O2 here? Well, okay. All right, so you have 11 plus 24, and then on the other side, you have 24 plus 11. Okay, so that's your balance equation. What's the change in moles, delta N gas? How many moles of gas after and how many moles of gas before the reaction? After the reaction, you have 12 moles of gas in the form of CO2, minus how many moles of gas before the reaction? 12, so 12 minus 12, so this is gonna be 12 minus 12, right? So that's no change in moles of gas. You remember how to get the mean temperature of the reaction? P mean is T initial plus 0.63 times delta T, right? 60%. To be more precise, what was this 0.63? This is 1 minus e to the minus 1, right? So let's calculate the mean temperature for the reaction. This is going to be for the unknown run. T mean, T initial, which is, what was our initial temperature? No, this is for the unknown run. So your mean initial is 24.205 plus 1 minus exp to the 1, negative 1, right? Times delta t, which is, we have our delta t somewhere from the graph right there. Okay, now let me make that not yellow because that's something you're gonna have to fix because you're gonna have a different initial temperature and a different delta t. Delta t is fine, but you can have a different initial temperature for your runs. Okay, so that's not a formula that's gonna remain unchanged when you make changes to this, to your data. Okay, so how do you calculate delta H of combustion per mole? What's the definition of H? U plus PV. So delta H would be delta U plus delta PV. For reactions, what's delta PV primarily due to? Change in moles of gas, right? But we know we can make the assumption that PV equals nRT. So delta PV would be delta N times RT. Remember, when we attach a delta U or a delta H to our chemical equation, that assumes you're looking at the product at the same temperature as the original reactant. So temperature is constant. So that's delta N gas RT. It's primarily due to the change in the moles of gas.
So temperature is constant in this?
Yes, because when you write a thermochemical equation, the value of delta H or delta U that you attach to that chemical equation assumes that you end up with products at the same temperature as the original reactants. And that temperature will just take as the mean temperature of the reaction. So this T that we're going to be using here will be the mean temperature. That's why we have to calculate that. Okay. Now, if you're confused because the temperature actually changed in the calorimeter, you have to realize that our calculation assumes that that would be the delta T that would restore that. Remember, we have that minus delta T in the formula because you're restoring the temperature back to the original temperature. Now, that doesn't really change very much the delta H over a narrow enough temperature interval. So whether you use T mean or T initial or T final in this formula or the mean temperature, you're gonna get more or less the same answer within the right number sig phase.
So delta PV is 0.
No, it's not because in this particular case, yes. Because change in moles of gas is 0. But let's make this generic. Let's just say this is gonna be equal to delta U plus delta N gas times what's R? We're doing kilojoules, so what's the unit for, what's the value of R in kilojoules per mole per Kelvin? 8.314, that's in joules. So if I want it in kilojoules, times 10 to the negative third, right? Times the temperature, and we're gonna use the mean temperature for the run. Okay? So it's basically the same because you're adding 0. But if you have a different reaction, remember when you did the simulations, you all got different compounds, so you're not gonna get the same delta N gas. So this is something you have to modify for your calculation. Okay. Now let's calculate the delta H of formation of the sample. So in this particular case, I'm interested in one. Delta H formation of sucrose, right? So my sucrose is let's make a generic formula here. CXHYOZ. Okay, because all your compounds have this generic formula. X, Y, and Z, solid or liquid, plus O2 yields CO2 plus H2O. CO2 is a gas, water is a liquid. Okay, how do I balance this? How many CO2s do I get?
X amount of CO2s.
Okay, so if I have X carbons here, how many carbons do I need here? So this has to be X. How many hydrogens do I have on the left? So how many water should I get? Y over 2. How do I balance my oxygen here? Let's call this W. What's my W here?
P minus 2x minus
Okay, Z plus 2W, that's on the left, right?
equals 2x plus y over 2.
Yeah, equals uh, equals 2x, the oxygen from CO2, plus y over 2 is the oxygen from water. So how do I solve for this W right here? W is equal to 2x plus y over 2 divided by minus z, right? Divide minus z and the whole thing divided by 2. That's how you can this is how you can balance the equation quickly using formulas. But anyway, let's tabulate those numbers. What's our x? Sucrose, okay, and H, how many hydrogens? 22. And how many oxygens? 11. Okay. So, how do you know, how do you calculate the standard the delta H for this reaction? If you could look up standard enthalpies of formation. Remember the formula from the lecture? Delta H of this reaction, which we measured experimentally, right? So this is delta H combustion, correct? We measured that. That's what we had here. That's the delta H of combustion per mole. Okay. So we know that. So how is the delta H combustion related to the delta H of formation? Products minus reactants. So X times delta H formation, delta HF of CO2 gas, plus, what's next? What's the other product? Y over 2 moles of water times the delta H formation of water liquid per mole times Y over 2 moles minus reactants, delta H formation of our sample minus W times delta H formation of O2 gas. Can we make a simplification here? I don't like that W. That looks complicated. But what do we know about O2 gas? It's in its standard state, so delta H formation of O2 gas is 0. So all I have to do now is just solve for this, right? So what's the formula for delta H formation of sample? I can move this over to the left, and I can move this over to the right. So I have delta H formation of my sample equals X times delta H formation of CO2 gas plus Y over 2 times delta H formation of liquid water minus delta H of combustion of my sample. So that's your formula right there. So what do I do now? Can I calculate it? Well, I have to know what the delta H formation of CO2. So where do I look for that information? NIST webbook. So let's do a search for, so go to webbook.nist.gov and let's look for, go to chemistry webbook. Let's look for carbon dioxide, CO2. CO2 is a gas. So you want gas phase data and then search, and there's CO2 right there. And there's the value for CO2. We're gonna use the value from the most
really, really fast.
I went really fast. Okay, let's try it. Let's backtrack. Okay, backtrack. And webbook.nisc.gov. Are you made it here?
Yes.
Webbook.nisc.gov. Okay, and then you go to NIST chemistry webbook. Okay. And then search for a formula. And then the formula is CO2. And then down here, you're looking for thermodynamic data for the gas phase, so you check gas phase.
Oh, you had to catch.
And then you click search. Okay, and then if you scroll, you'll find the delta H formation of carbon dioxide gas right here. So let me take a screenshot of this. Control Windows Shift S. And then I'm gonna take a screenshot here. Okay. And then paste that in Excel. Okay. A little smaller. So what's the value? We're gonna use 393.52 kilojoules minus 393.52. Okay. And where's my source?
Wait,
Yes.
why did you choose 0.52 instead of the top one?
It's 1998, the more recent one.
Mhm.
That's it's plus or minus 0.13 anyway. So the top one. And our source in this case, we'll just copy the link right here. Control C to copy that link. And we're gonna put that link over here.
And you went to webbook, not the source that it used.
Yeah, because when you go to the webbook, you can go to the primary source from there. All right. And when you paste it, it just gives you the title of the page. The title of the page here is carbon dioxide right here. So, but it is actually a link. So if you right click on it, it tells you what the actual link is. Right click, edit hyperlink, it tells you what the actual link is down here. So if it's clickable.
I did it myself.
Mine's a big giant.
That's fine. It gives you the full link.
Yeah.
Yeah. Sometimes I like the full link, sometimes I just like the title. But you know, if it's as long as there's a link. All right, so that is your carbon dioxide. So what would it be for water? So you just go click on the back button here, go back to your NIST search page. Yeah, and then you go, and for your formula search, you search for H2O. And this time you want to do condensed phase, not gas phase, right? And then search, and the value for liquid water, right here. Control Windows Shift S to bring up the screen snipper. And then liquid water right here is negative 285.83. And I'm gonna paste it in my Excel document. Okay. Minus 285.83. All right, and my source, I'll just take the link, copy the link, Control C, and paste that link here, and it's just gonna tell me it's water. So are you still with me? pause it for a bit. Recording. Okay, so standard delta H of formation of the sample from the experiment then would be what? What was your formula? Right here is X times the value for carbon dioxide, right? Plus Y over 2 times the value for water minus our experimental delta H of combustion. So let's go ahead and put that in. This is equal to X, which is 12 here, times the value for carbon dioxide, which is negative 393.52, plus Y over 2, so parenthesis, Y divided by 2, times the value for water, which is minus 285.83, minus the experimental delta H combustion, which is B34, right there. Okay. And you should get minus 1973.53. And you can compare that with the literature value. Can you back the formula one more time? Okay. It's 12, which is X, times the value for carbon dioxide, plus Y over 2, which is 22 divided by 2, times the value for water, minus B34, which is the actual delta H combustion we got from the experiment. So this is our experimental delta H formation. So this is how those tables of delta H formation of organic compounds were constructed. You just burn all these compounds. From the combustion, you can get delta H formation. Okay. Now, let's compare that with the literature value. I had this originally for fumaric acid, and then I realized I assigned fumaric acid to one of you, and that would give that student an edge. So you know who you are. You all got different unknowns for the simulator, right? One of you got assigned fumaric acid. That's why in previous years I did fumaric acid. So
Yeah, all the standards. That's why we're.
you all did the standard, and you each did a different unknown. Yeah, you did.
For the simulator.
For the simulator. Now, because I want you to work this out for the simulator. You cannot do this for your lab data because your lab sample, the unknown sample in the lab, is not a pure sample. It's actually still benzoic acid in a capsule, right? So it's not pure. So we can't get delta H combustion, or we cannot get delta H formation. We can only, for your lab data, you stop at delta H combustion. Okay. So this is just this is for the simulator part of the activity from 2 weeks ago. So what's the literature value for sucrose? What do I do?
C12, H22.
Or to be sure you're really getting, there's a lot of C12, H22O11s. There's a lot of disaccharides, right? So you search by name instead.
I like that better.
Search by name and you just type sucrose. And then you want condensed phase. And then search. And there's sucrose right there. And delta H formation of the solid. Let's take a screenshot of that. Windows Shift S to do the screenshot. And let me copy the combustion values as well, because you'll notice here there's the delta H formation and there's delta H combustion, right? Let me put the literature value here. So remember, we are calculating delta H formation from experimental delta H combustion. So where do you think this delta H formation of solid here, what do you think the delta H combustion was for the experiment that led to that number? Which of these combustion numbers? This was done, this is referring to Clark and Stegeman. So It must have been calculated from the value here from Clark and Stegeman. That's my assumption. Unless they averaged it or something, but it's referring to Clark and Stegeman, so that's got to be delta H formation from their value of the delta H combustion.
Do we have to have all that in our screenshot, not just the delta H formation?
Delta H formation is fine. I'm just bringing it up to you that you can see the variability of so you can see the variability of the numbers that are obtained from experiment. Okay. Delta H formation of the solid, that's what we're comparing it to. So this is minus 2221.2 kilojoules per mole. And our source here is this website. I'm gonna put that over here. And so what's our percent error?
Negative 11.15.
Negative 11%. Okay. So equals experimental, this is our experimental, minus the literature divided by the literature value. So 11.15% error.
Not multiplied by 100.
Multiplied by 100, thank you. And 11% error. What's the percent error for, just out of curiosity, let's calculate percent error for delta H combustion. Let's use Clark and Stegman's number. What would that be? Experimental value would be, again, this time it's going to be combustion, right? Minus 5892.84 minus the experiment, the literature value, which is negative. So plus, so that becomes plus, minus, and then I'll put it in parentheses, 5644.17 divided by negative 5644.17 times 100. Ah! That's big. No, minus negative 5644. Okay. That's 4.4%. Why is the percent error different? Why is it bigger for the delta H formation as opposed to delta H combustion? Same data source. The reason for that has to do with when you're comparing it to a smaller number here with delta H formation. So that errors. So you have the same absolute error basically. This one. This one. Oh, the last one. Yeah, this is just delta H combustion, the experimental value minus the literature value from Clark and Stegman.
Can you go to the 1973 yellow one?
This one?
Yeah, it's different.
Okay. So that's X times the value for CO2 plus Y over 2 times the value for water minus the delta H combustion. All right. So let me stop the recording here.